Yes, so thank you, first of all, for having me. This is my very first Rust conference. I'm quite new to Rust, so that's exciting. And I also grew up not too far from here, so close to Vienna. It's always nice to be back in the region. This talk is about incorporating Rust for audio on the web, hopefully with some practical takeaways. And that up on the screen is me a long time ago. I was focusing on producing electronic dance music, playing shows, etc. And with hindsight, that was a very special time. I managed to catch a very tail end of an era, just as smartphones, social apps, streaming platforms, etc. began to reconfigure our world more or less completely. And whether we like it or not, software is increasing the substrate that we all operate on. There used to be a bit of software in music for making music. Now there's a lot of software with a bit of music sprinkled here and there, and software is governing how music is presented, distributed. So I think already back then it was kind of obvious, this pattern. I felt very strongly that I needed to learn how to do software, understand programming, very much in the spirit of having more creative agency or control over how our work was presented. So that's what I did. Haywires, which is my company now, it originally started out as an independent, small boutique record label. It was meant to be a sort of a creative container for both my music, but also music of my peers. And the idea was to explore newer ways of releasing music with this maybe lofty goal or dream of eventually being able to publish music as independent, interactive websites. So now I'm standing here a decade later, so it's fair to conclude that I kind of got sucked in. Haywire somehow morphed into a more normal software company. And along the way, I had the chance to work on a bunch of systems, interconnected complex systems, sometimes having to figure out reliable ways of dealing with millions of requests incoming per second. And these systems are still in place long after I left them and my colleagues left them, just chugging along. But I guess what I'm trying to say with that is that software is important, software is real, and the way we do software matters. So this is where Rust comes in. But music matters too, and I did not forget about that original seed, or original idea, so I kept on working on it to the extent possible on the side, channeling what I learned and the resources into building out this service called SongSling. It's sort of an internal R&D project that I hope will launch in the near future. There's still a bit of work to do. And this video is silent, so that's cool. But I just put it up so you could get a feel for the interface. So this is a web app. It's an audio workstation / game engine on the web. But the context we're dealing with is the browser. And there's interesting thing when it comes to browsers. So let's just start with this small example. This is a piece of JavaScript code, and I think if someone showed me this essentially one-liner years before, I would have started programming much earlier. So all it does is changes the background every 3 seconds, and it's deceptively simple. And that's because the browser provides us with all these interfaces that our scripting language can hook into. If you try to do the same thing with Rust, it gets a lot more complicated. So I tried to make something that would work similarly in Rust, and so it's a few more lines. But if you look under the hood, you would open a can of worms. There's a lot of complexity, and we have to deal with WebAssembly, foreign function interfaces. We need to do with memory management, all kinds of interoperability issues. Debugging is hard. And there's also a lot of bloat. So with auto-generated bindings for these couple lines, you would end up with hundreds of lines of code. And what I was also very surprised for when I just started I remember like a very first test I did, just trying to get something compiled to WebAssembly. I was shocked at the bundle size, which was 1.3 megabytes, so more than all the JavaScript code for the entire app. And it's also important to note that it's performance-wise, WebAssembly is only sometimes faster. The main benefit we get here is it's more predictable. And in the context of audio specifically, there's some good news because we don't really need any frameworks. We don't need to deal with any of the harder stuff when it comes to Rust. No async, no strings. Don't really need generics because everything is just floats. No multi-threading in Rust. And sort of zooming out a little bit and we'll move inwards, I wanted to spend a bit of time on talking about audio. So audio as a domain is less forgiving than pretty much anything else we typically deal with on the web. So in a typical application developer mindset, events come in and they trigger immediate reaction or state changes. Just as in case of this interval timer code, we just change the color and we are done. But in audio, we are dealing with a continuous stream that also has a built-in delay. So there's the physical delay, the time the sound waves reach our eardrums, but also a built-in delay in terms of the software and the hardware interfaces we need to work with. So what we're hearing at any moment has already happened. The final data was handed over to the audio interface many milliseconds earlier. And if an event comes in, it has to consider like the history and the timeline and the schedule of the continuous stream. So when you compare it with graphics, a very smooth experience, 60 frames per second. Actually, it's a lot of time in terms of software. You get 16 milliseconds to draw something on the screen. And in theory, that could accommodate a lot of things, even maybe round trips within the same data center. It's not a good idea, but in theory, we could still do that. With sound, if you're talking about the sampling rate of 48,000 hertz, then we get 20 microseconds for the next sample frame. And now we usually buffer these, of course. So you work with what's called the render quantum in web audio spec parlance. So that's usually, let's say, a buffer of 128 frames. So that kind of bumps us up to a window of maybe 2.6 milliseconds or so. But we have to meet that window, right, for processing. So anything we miss, if we miss one frame, we will hear it as clicks and discontinuities, artifacts. So we don't want that. And on top of that, there's also the environment we're dealing with in terms of the browser. Normally, audio workstations run as applications on top of an operating system, so they can request high-priority threads. But if you're in this JavaScript realm, we kind of have to work with whatever the browser gives us. And if we want to incorporate WebAssembly, then we still have to talk to this little JavaScript interface going back and forth. So yeah, the situation is not that easy on the web. And remember, we only have that 2 milliseconds roughly to deal with the output. So the question is, how can we run custom audio code that's guaranteed to have a predictable, regular processing window on the web? And is it even possible? So let's try. Could it work? First of all, shout out to my friend Stuart Waite, who made this amazing model. We call this the beast of two indexes. So I hope that was enough for your ears. Yeah. So what I kind of tried to do is replicate that experience of working with a turntable, and that's also at the very core of SongSling. So I miss this time when you could touch the music and kind of have direct control over playback speed, and you can fast forward, you can rewind. This is a feature in common, audio players that just kind of disappeared with digitization because it's just so much easier to do it. And the name, the beast of two indexes, comes from the fact that we're dealing with a lot of ring buffers in audio typically. So there's a saying in game audio that any kind of engine code resembles a sampler instrument, and in my experience, that's true. It's a really complicated sample instrument, and this beast that's kind of like always biting its tail and a head can come at you at any level. So how does it work? In terms of audio on a web, we have two options. One of them would be to play out files or streams via the normal media elements, so you maybe know the audio or the video HTML tags. And actually, that's quite good these days because we have something called media stream extensions. So you could construct custom streams and pipe them through those elements. The problem is that we don't get to schedule things precisely in terms of the audio stream at audio rate. So for that, we have to use the Web Audio API. And it allows us to create a so-called audio context. You define your sampling rate, your outputs, you create a context. And you get a set of built-in nodes, which can be linked into a processing graph. So you can wire the inputs and outputs. You can even wire the output of one node into a parameter of another. So you can construct relatively complex graphs. And there's this notion of the control and rendering thread. So the rendering thread is an actual real thread, an actual process thread where the browser handles audio. But we only get to interface with the so-called control thread, which is exposed to us as a JavaScript API. And there's only one single place where we can plug in custom processing code, which is the audio worklet. So it's a class that we need to, JavaScript class that we need to extend. We can define our own parameters, the number of inputs, outputs, and we can register it as a module that will be run inside that rendering thread. And this is also where we get to insert Rust. So in case of the little demo that you showed earlier, it works in a way that the audio processing is done on the audio worklet node, but the data processing is done in another worker. And that's because it's always a good idea to try to isolate everything that's related to audio code into its own world, so we could banish this weird lizard into its own context and fence it off. But we still have to deal with the main thread, because the web audio graph, the so-called control interface, lives there. So there's a proposal to allow it in workers, but it will take probably a few years to implement. Ideally, we'd want to have this little box inside the audio engine worker itself. But other than that, this will work, and we do get some kind of guarantees when it comes to the audio workload. So that's the only place where we can hope, we have a well-founded hope of our processing code being executed in regular chunked intervals. Now, of course, you have to communicate between them, and there's two ways to do it. So the default way is using post messages. And they usually work quite well for all the other use cases, but there's a problem with garbage collection. So if you send a lot of events, a lot of messages to the audio worklet, of course it will eventually trigger garbage collection, and your window of opportunity will be ruined. So you're kind of stuck with the other way, which is a shared array buffer. That's a shared view and memory between threads. And this is usually the place where most web developers, including me, so this is the first time when it forces you to think about how data is really represented inside a computer. So normally in the web world, you only need with JSONs. Maybe you get some protobus, but there's all this auto-generated code that kind of abstracts it away from you. Here, you're kind of forced to deal with how do you want to serialize your state. And there's a lot of things you could do. So one day, I found myself writing these really weird helper functions, and this was the moment when I realized, okay, maybe I outlived the language of my choice. And if you end up simulating a lower level systems language in a scripting language, it doesn't make much sense. So this is, I believe, Coro. This is where WASM and Rust comes into play. We need to deal, when it comes to WebAssembly, we need to realize that both JavaScript and the WebAssembly world will share a memory object that they can both read and write to from. So in terms of our processing code, we want to make sure that we kind of allocate pointers inside Rust, but keep track of them on the JavaScript side. And ideally, we only do this in the constructor, so we never touch this again, or at least this is the way I found. And then you kind of pass these pointers back to in a process script, which will get called in this render quantum, so every 1 or 2 milliseconds. You only do processing. You kind of pass in the parameters back to the WASM world, the Rust world. And so this way, you're already getting to unsafe territory because you have to pass the pointers over a foreign function interface. Here I'm using what I looked up in the docs called manually drop. I think you could also use core, like memory forget, but apparently this is the canonical way. So you pass over this pointer, and then in the process code itself, you get them back, and you do all your magic. So manual drop is needed so that, basically the memory doesn't get deallocated or destroyed at the end. The destructor does not get called. And a couple other tips, maybe that's a more generic takeaway, that you don't need the standard library on the web, right? Because you're already running within this hosted environment. You can take some cues from the embedded world and remove that. You can, first thing I did was obviously, you could do optimizations in Cargo, where you strip all the debug information to decrease your bundle size. You can enable link time optimization, which will help remove that code. And one other thing is using custom allocators for WASM. So a lot of guides in the wild suggest valloc, which is unmaintained. I think there's a report out there about it. Leaks, which is not necessarily a problem, as we see later, but still, you could use talc instead if you need something more robust and custom, or mini alloc, which is really tiny. It's just a simple bump allocator. And ideally, we only ever call these allocation once, so inside our AudioWorklet constructor. So hopefully, everything lives with the audio context and doesn't need to be dealt with again. For optimizing WebAssembly bundle sizes, there's a couple tools out there. Obviously, binary end toolkit, WASM WASM strip is quite useful. Twiggy for profiling code sizes. And the really interesting one is the shrink part of WASM tools, which allows you to pass in a predicate. So you could shrink down your WASM code until it either fails or passes whatever you pass in, which can be helpful, I guess. And as one of the closing slides, in terms of audio crates, there's some stuff out there. I don't use any of them. I'm kind of trying to build everything. It's R&D, so it's all from scratch. But the ASP looks really good. It's no standard library, no allocations. It just gives you building blocks and kind of allows you to remain generic over your audio processing graph. There's also Fun DSP, which is another one. Rust FFT is a crate that does Fourier transforms with SIMD. So if you're really adventurous and want to try to play with some experimental WASM features, you could do that. MIDI-R is useful for handling MIDI events. You can also use Rust code, of course, in the other worker. A really interesting one is the Web Audio API implementation in Rust by Otto and Benjamin from the Web Audio community. It's quite a heroic effort. They re-implemented the entire Web Audio API in Rust, so it allows you to keep the same graph or the same constructions and run them outside of the browser, or even go meta, and through CPA you can kind of wire it back in a browser. Yeah, that's all I have, I think. Thanks for listening. I always end with this slide. It's important to point out that a lot of audio stuff is C++. There's not enough Rust out there, I find. I could probably count it on one hand, people who deal with Rust and audio. And it would be nice to change that. So if anyone's interested in that, feel free to reach out. And I hope Rust will be part of this new line of slowly moving into an era of interactive music. Thank you very much.